Hello, this is the last example of section 3.3. Find the maximum and minimum values, if they exist, of c equals x plus y subject to the following constraints. Um, Let me go through. We're just going 20, 20 this time. That'll be sufficient. So we get find our feasible region first, so graph our boundary lines. Using the cover-up method, we get an x-intercept of 4, 0, and a y-intercept of 0, 6. And then x plus 3y is equal to 11. Oh, this one's not going to be nice. But we get an x-intercept of 11, 0, and a y-intercept of 0, 11 thirds, which is a little bit less than 4. So go 11, and then a little bit less than 4. And then the x greater than 0, y greater than 0, we get in the first quadrant. So if I do a test point of 1, 1, well, 3 times 1 plus 2 times 1 is 5. 5 is not bigger than 12. So 1, 1 does not work. But how about 5, 5? Well, 3 times 5 plus 2 times 5 greater than 12? Yes, it is. 5 plus 3 times 5, is that greater than 11? Yes, it is. Is 5 greater than 0? Yes. Is 5 greater than 0? Yes. So, our shaded region, don't forget we have to stay in the first quadrant, is this. So the reason why this is different than all the other ones we've done is it's not bounded anymore. So remember, if you read the definition, we may not have solutions this time. But if we're going to have solutions, they still have to occur at the vertices. So our vertices, well, we have a vertex here, but then it just keeps going forever in a line. So that's the only vertex there. So that is 6, or sorry, 0, 6. We have a vertex down here, or a vertex down there. So that's 11, 0. And then we need to find this intersection point between the two lines. And I actually think I just drew my lines poorly because it looks like it's at 1, 4. But I think it's at 2, 3. So I just drew my lines poorly. But instead of trying second guess, let's go ahead and solve it. Let's call this A, call this B. If I multiply B by -3, so I want to do A minus 3B. So 3 minus 3, 0. 2 minus 3 times 3 is -7. And then 12 minus 3 times 11, -21. Divide by 7, we get y is equal to 3. Plug it back in, we get x plus 3 times 3 equals 11. Get x plus 9 is equal to 11, so we get x equals 2. So that was correct. It's 2, 3, not 1, 4. Now plug it back in. We get c is 6, c is 11, and c is 5. So you might say our minimum is 5 and our maximum is 11. Now, just like at the beginning of the notes, I am going to use Desmos now to explain why that's not true, and then I'll show us a by hand way to do it without Desmos. So let me bring Desmos back up. So here is kind of what our, let me actually change this. The reason why it doesn't look exactly there. Now it looks like what we have shaded. So that's what it looks like our shaded region is. But now when I do this, you'll see, oh, let me change it to 50 instead of 200. That was quite too big. That our plane is going up forever. So, because it's going up forever, there is going to be no maximum value, but there is a minimum value. And it looks like the minimum occurs here, which is at that 2, 3 location that we found. So our answer is C has min of 5 at 2, 3. C has no max. But how can we do this without using Desmos? Well, what you have to do is, because what I just shown you, the plane is either going to go up, or depending on the slope of this plane, it could actually go down. So if this plane had went down instead of up, then there would have been a maximum of 11 at 11, 0 and no minimum. So how do we determine if it goes up and down? Well, you just pick a point like way out here and see what happens. Actually, so let's pick the point. Well, actually, I'm just going to pick 2020 because it's the easy one to pick. So 20, 20. Well, 20 plus 20 is 40. So I see that's much larger than all the rest. So that's indicative to me that my plane is on an upward slope instead of a downward slope. So there would be no maximum, but we do get a minimum. And that is it for section 3.3.